Hall effect. This is one of the most important question for the same examination. So let me define you what is meant by Hall effect, and then we can see the derivation of this Hall effect. Hall effect is the phenomenon by which electric field is induced in a semiconductor slab carrying a current placed in a transverse magnetic field, and the induced field is in the direction perpendicular to both current and the magnetic field. సో సింపుల్గా డెఫినేషన్ ఏంటి అంటే ఒక సెమీ కండక్టర్ స్లాబ్ని కన్సిడర్ చేస్తాము. సో ఇన్ దాట్ వీఆర్ గోయింగ్ టు ఇంట్రడ్యూస్ అన్ ఎలక్ట్రిక్ ఫీల్డ్, అండ్ దిస్ ఎలక్ట్రిక్ ఫీల్డ్ ఈజ్ ఇన్ పర్పెండిక్యులర్ డైరెక్షన్ టు ద కరెంట్. సో ఒక సెమీ కండక్టర్ తీసుకున్నాం, అందులో కరెంట్ అండ్ మ్యాగ్నెటిక్ ఫీల్డ్ అనేవి పర్పెండిక్యులర్ డైరెక్షన్లో ఉంటాయి, అండ్ వీఆర్ గోయింగ్ టు ఇంట్రడ్యూస్ దిస్ ఎలక్ట్రిక్ ఫీల్డ్ ఇన్ ద డైరెక్షన్ ఆఫ్ ద మ్యాగ్నెటిక్ ఫీల్డ్. సో మ్యాగ్నెటిక్ ఫీల్డ్, ఎలక్ట్రిక్ ఫీల్డ్ ఒక డైరెక్షన్లో ఉంటాయి, అండ్ ద కరెంట్ ఈస్ పర్పెండిక్యులర్ టు దీస్ టూ ఫీల్డ్స్. ఓకే, నౌ దిస్ వాజ్ అబ్జర్వ్డ్ ఇన్ 1879 by Edwin Herbert. Hall discovered, so it is known as Hall effect. It occurs in conducting materials such as metals, semiconductors. So for the derivation, let us consider that let I be the current that is in x direction, and B is the magnetic flux density in the z direction. Let me show you the diagram so that you can understand. So this is the semiconductor slab we are considering. So the current is moving in this direction and the magnetic field is moving in this direction. B represents the magnetic field. So in this direction we are going to introduce the electric field, and the resultant force is in the direction of negative axis, negative y axis. So the direction, the resultant force will be in the negative y axis. So this is the y axis. In the opposite direction, the resultant force will be there. In n-type semiconductor, current is due to electrons, and these electrons are so here we are considering an n-type semiconductor, and the current is moving in this direction, and the current is due to electrons because in n-type there are more number of electrons from A1 to A2 side, and side A2 to negatively charged. So this is the A1 side, this is the A2 side. Here we are considering that A2 is negatively charged, and it is a n-type semiconductor, and current is due to electrons. The process leads to the existence of potential at A1 and A2 because here we are considering that A2 is negatively charged, so there will be a potential difference. So the electric field will move from higher potential to the lower potential. So let it be represented by the, so here we are considering that there is a voltage difference right in between A1 and A2. So let us name that voltage difference as VH. VH is known as Hall voltage, and the force due to I and B produces electric field. This electric field due to Hall effect in turn exerts a force on the charge carriers in equilibrium state. Here I and B are in perpendicular directions. Because of these two charges there is an electric field. So here from this we can, the forces F is equal to EE. F is equal to EE, where capital E electric field is equal to BV. This is from Lorentz force. So from that definition we got this B into V. V is the drift velocity. So from this E is equal to BV, where E is the electron charge. I hope this is clear for you. So here we consider a semiconductor having A2 as a negative charge. Here we are considering that A2 as negative charge, and the length is A, breadth is B, and magnetic flux is flowing in Z direction. I is in this direction current, and the resultant will be in the opposite to the y axis. And let us consider that there is a distance between A1 and the A2. So what is the distance between A1 and A2? The distance between A1 and A2 is B. So up to here we got E is equal to BV and F is equal to EE. From that we got F is equal to BEV. So as we know that B is the distance between the A1 and A2. From this, voltage is equal to electric field into distance. So VH is equal to Hall voltage is equal to B into E. We already know that J, current density formula is rho V, volume charge density into velocity. We already know this formula, and also we have current density formula is current per unit area. So I into A. Area will be length into breadth, A into B. So from this equation, VH is equal to BE. We have VH is equal to BE and E is equal to BV. So here, from this we have J is equal to rho V. So from this, V is equal to J by rho V. So J by rho V. So from this, J is equal to I by A. So from this, J is equal to I by A, we are substituting in place of J, I by A. So J is equal to I by AB. Here we got J is equal to I by AB. So in place of J, we are substituting I by AB, so that this B and this B will cancel. We will get BI by rho V into A. So from this, VH Hall voltage is equal to magnetic flux B into current, rho V volume charge density, and A is the length of the semiconductor. So by knowing all these values, we can know the Hall voltage. So if the Hall voltage is positive at A1, the carriers are electrons. Hence rho V is equal to Ne. If so, here we have two cases. If the VH value we got after calculating, after knowing all these values, if the value is positive, then we can say that it is positive at A1. If not, it is negative, and the charge volume charge density is number of electrons N into E, and if the charge is positive, then the number of holes into the charge E. So these are the two formulas. P is the hole concentration, N is the electron concentration. So this is enough for the Hall effect, and mention that P is the hole concentration. So if they asked about, write about Hall effect or the derivation, this is enough. So here we have some more things, that is definition of the Hall coefficients Hc. So the Hall coefficients is defined as the reciprocal of the charge density. So the charge density is rho V, which we got volume charge density rho V here. So Hc is equal to 1 by rho V. So the rho V value we got is Bi by Vha. So the reciprocal is Vha by Bi. So we already know that the conductivity is volume charge density into mobility. So from this, we are substituting these values. So here rho V is equal to sigma by mu. So as it is reciprocal of the 1 by volume charge density, so it will be mu by sigma. Hc, Hall coefficient, is the reciprocal of charge density. So the charge density is rho V is equal to sigma by mu. From this, mu by sigma. In semiconductor, the Hall coefficients where condition is due to both electrons and holes. So we already know that the mobility formulas which we have learned before. So that is P into mu square P minus N into mu square N. And the conductivity sigma is formula is E into the charge E or Q, N mu N plus P mu P whole square. For intrinsic semiconductors, the number of electrons will be equal to number of holes. So if we substitute this N equal to P, then if we consider that P equal to N equal to Ni, then we can get that Ni into mu square P minus mu N square. And so this is the Hc for the intrinsic semiconductor. And for the extrinsic semiconductors N type and the P type, RH and Hc will be negative in semiconductors, or Vh will be the negative. So for the N type semiconductor, the number of electrons will be more in number. So RH is equal to, it will be negative minus 1 by Ne, the reciprocal. And for the p type, the holes will be in maximum number, so it is the reciprocal of the volume charge density, so that is 1 by rho e. So here VH is positive, here VH is negative. So this is the Hall coefficient. If they ask about the Hall effect, writing up to this, writing up to here is enough, but if they asked about the Hall coefficients and all, then you have to write out all these things. And the applications of Hall effect, here I have mentioned 4 applications of Hall effect. You can also Google some more applications. So it is better to write the applications of Hall effect at the end in the question. So if you do any mistakes in the derivation part also, so these applications will save you. If not, in 2 marks also they may ask you about the applications. So the applications are, it is easy to determine whether a semiconductor is p type or the n type, because we can get the values of VH and RH. Maybe it may be negative or positive. So if it is negative, then we can consider that it is a n type. If it is positive, then it is a p type. And find the carrier concentration, conductivity and the mobility. So these are the applications we have.